All right, Pre-Calculus 30, 11.3. This is the last section of the textbook. I don't know if this is the last section for all of you that may be watching this video, if this is the end of the school year for you, but it is for us. And it's entitled the Binomial Theorem. So what we're going to talk about is we're going to talk about patterns of expanding binomials. So you know what a binomial is, right? A binomial is any expression with two terms. That's a binomial right there. Bi means two. And if we were asked to expand this binomial, okay, this expansion, we know how to do this, right? This is like the FOIL method, right? So let's write this out just as a refresher. That's what it looks like. And we're going to do the FOIL method. So some of you learned that and you like that. So a times a is a squared. A times b is plus ab. B times a plus ba, and then b times b is b squared. You combine all the like terms here, which ab and ba are like terms, so that's a squared plus 2ab plus b squared. All right. Now, that's something that we know, and the FOIL method is something quick that you can do that in your head by now. It gets a little bit trickier when we up this exponent. Okay. Squared is not a big deal. Cubed is not a big deal either, but it's a little bit more of a big deal than the squared, right? I mean, so we do have to do a little bit more expansion. So let's just do that one here and see how that goes. Now, what you have to remember, and here I'll just shorten this up just a smidge for you, but really this is the same as this, isn't it? A plus b cubed is actually a plus b times a plus b squared, right? Because really we have the exact same bases here, and so what we do is we add the exponents to simplify this. So you could think of it this way, and for the purposes of this lesson, just to shorten it up a bit, I am going to show, just take away one step, and so really this looks like this, doesn't it? Okay, and so as we expand this, it's going to look, I'm just going to give myself a little bit more room here. So now, it's not really FOIL method, but it's distribution, isn't it? So that's going to be a cubed there, and that a has to distribute to all of them. So plus 2a squared b. And then finally to the final one there, that's plus ab squared. Now we have another a squared b as we kind of distribute this one along. Plus 2ab squared plus b cubed. Gathering like terms, well, we have a cubed all by itself there. Is there an a squared b term? Yep. Look at that. So this is, you guys with me? 3a squared b. And what about ab squared? Yeah, we have two of those, so that's another 3ab squared. And then we have 1b cubed. All right? Now, just with those two examples, okay, actually, I will add a third, actually. I'll add a third. Okay? It's a little bit out of order. But can we expand this? Yeah, I could have started with that, but I didn't want to totally mess you up there. It's like, what is he doing? But really, a plus b to the power of 1 is just a plus b, right? Okay? So right now, we can recognize some patterns. And if you've read this already and you're like, where is Pascal's triangle here? We're getting to that. But I just want you to notice a few things before we start this whole lesson. Okay? If we have a binomial to the power of 1, we have two terms. If we have a binomial to the power of 2, we end up with 3 terms. And if we have a binomial to the power of 3, we end up with 4 terms. Okay, so there's your first recognition of a pattern. Okay, is that when we are expanding binomials, we always have, and if this exponent is n, okay, and I'm not ready for this yet, so I'm just going to make some room there. If we have a plus b to the power of n, and we expand that, we always have n plus 1 terms in the final expansion. And of course, the expansion just means we're going to multiply it out. Okay? So that's the first. Any other patterns that you recognize or want to take a guess with here? Just with a plus b to the 1, a plus b to the 2, a plus b to the 3. Anything else that you notice? that could be connected to the particular expansion? Anybody? No? Really? Some of you aren't even looking up at the screen. Any other patterns that you notice here? Okay, the highest degree in the finished expansion, in the final expansion, is the same as the exponent. Yeah, look at this. This is a 2. Guess what? This is the highest degree of any variable term. And as a matter of fact, you could even follow this along and say 3 here, and we have, oh, I can't even see my cursor there. And 3 there, and where is it over here? 3 over there. I don't like that yellow anymore. And look at this, 1, 1, 1. So we start off with the first term to this power, always. You see, the first term to this power. We have it there. The first term to this power. We have it there in the expansion. And we always end up with the last term to that power. The last term to this power. See, over here. And so on. The last term to that power. So that's another pattern. Let's write that down. Okay? First term is a to the n. Last term is b to the n. Yeah, very good, very good. Okay. Now what I want to focus on here, what I want to focus on now is the coefficients, okay? The coefficients of the expansion. Okay, these are the coefficients that I'm sort of outlining here, and of course where there is no number that's understood to be 1. All right. And just for kicks too, I'm going to show you another expansion. All right, what is a plus b to the power of 0? How does that expand? A? Just A? Just B? 1. That's right. As long as this is not 0 to the power of 0, but yeah, this is 1. Doesn't matter what the terms are, what the values are, unless they're both 0. This is 1. Okay. So look at these coefficients now. Right? We've got 1 for a plus b to the power of 0. For a plus b to the power of 1, the coefficients are what? Well, they're 1 and 1. For a plus b to the power of 2, what are the coefficients? Where is it? 1, 2, 1. So I'm just going to list those here. 1, 2, 1. What about a plus b to the power of 3? What are the coefficients there? 1, 3, 3, 1. Okay. 1, 3, 3, 1. Any patterns that you're noticing there? Now, if you've never seen this before, it might be a little bit tricky, but let's go back up here. What are we going to be talking about right now? Pascal's what? Triangle. Have you ever done a pyramid? You know, where you get 4 people on the bottom, and then 2 people or 3 people go on top of them. You know, hands and knees sort of thing, and then another 2 people and one person. You see the triangle here? You see this triangle? Okay. Look at this. Each row starts with a 1 and ends with a 1. See that? And what about these numbers in the middle? Check this out. Are you seeing a pattern there? The numbers on the ends are 1s. The numbers in the middle come from the sum of the 2 other numbers that would be sort of on top of it in this number pyramid, right? So let's make a guess here. A plus b to the 4. Okay, from what we know here, a plus b to the 4, what should the first number be, do you think? 1. Very good. Now what's the next number? 4. That's correct, because we're looking at this pattern. Now, what's the next number? 6. It is. and the next number is 4, and then it ends with a 1. Very, very good. Now this is something special called Pascal's Triangle. Pascal's Triangle. Okay? I believe it was Blaise Pascal, in 1653 came up with this array of numbers. And the reason why we study this, the reason why this is special, is because this triangle, if you continue this pattern indefinitely, the numbers in this triangle for each row represent the numbers or the coefficients in for each term in the expansion of this binomial. So remember, we just outlined the coefficients here. For a plus b to the power of 3, it's 1, 3, 3, 1. Those are the coefficients for the terms. So a plus b to the power of 3, 1, 3, 3, 1. Okay? So for a plus b to the 5 and so on, you're doing 1, you're doing 5, you're doing 10, you're doing 10, 5, 1. You see that? And we also have a bit of a symmetry down the middle, don't we? Okay, you see that symmetry? There's symmetry on either side. Where there's an odd number, we have a number in the middle, but everything is the same on either side. Where there's an even number of numbers, then there's a line right down the middle, and it's symmetrical about this middle line. See that? So putting this all together, this is one way to identify the coefficients in a binomial expansion. So if we put this next note up, you can use Pascal's triangle, and I'm going to get to this part in a second, the combinations part, but Pascal's triangle can be used to determine the coefficients in the expansion of, and they use different letters here, x plus y to the power of n, where n is a natural number. So we're not talking about fractional exponents, we're not talking about decimal or negative exponents. Okay? N is a natural number, the lowest of which could be, technically 0, so I don't know if natural number, I guess. Whole number really would be a better description, to tell you the truth here, because we can do to the power of 0. So I'm just going to change that for now, because we can look at a plus b to the power of 0, although, it's part of the triangle. Okay. Now, what about this other side here? In 11.2, we talked about combinations. Okay? Combinations. On your calculator, if you just get your calculator out here, you have an NCR button, right? An NCR button. Now, on my calculator that you see up on the screen here, it's a little bit trickier to get there. But let's say I did 5, and I'm going to choose 1. What's 5 choose 1? That's going to be 5. Okay? What's 5 choose 0? What's 5 choose 0? Is 1. Okay, good. You guys are faster than me. 5 choose, what did I say? 0. Come on now. Is 1. Okay? So we got 5 choose 0 is 1. 5 choose 1 is 5. Let's go up here. 5 choose 2. Let's do 5 choose 2. What do you got? 10. So we've got 0 is 1, 1 is 5, 2 is 10. 1, 5, 10. What's 5 choose 3? Whoops, it's an error apparently. Oh, 3. Hit 3. It's 10. So we've got 1, 5, 10, 10. Is anyone recognizing anything here? 1, 5, 10, 10. So what did I do? I did 5 choose 0. We did 5 choose 1. We did 5 choose 2. And we did 5 choose 3. What do you suppose 5 choose 4 might be? Let's double check that. Is 5 choose 4? Yes? This is so frustrating, this calculator. All these button pushes here. 5 choose 4. It is 5. And then 5 choose 5 is 1. Okay? So, if we start off with n, and it's getting a little busy here, but n right here. If we start off with n, and then we choose at a time 0, and then go all the way to n, we also can have determine quickly the coefficients for the binomial expansion. So in this row, okay, where the power is 5, we can use combinations to determine the coefficient. So that's this second part. We can use combinations to determine the coefficients. Okay. So again, why are you doing this? Okay. Why are we doing this? Well, if I said, what's 2y minus 3 to the power of 11? You'd go something very complicated. A big, long polynomial, which I have no idea what it is, but I'm not going to multiply that out, Mr. Maxwell. Because you'd have to multiply 2y minus 3 times 2y minus 3 times 2y minus 3 times 2y times 11 times, right? So would not be a good idea for us to know if there's any shortcuts. Okay? So this is why we're doing this. We're doing some shortcuts. Because you do not want to manually expand this puppy out right here. It's not going to be fun for anybody. So if I can figure out how I can write that expansion using mathematical patterns, that's what we're doing. So we would know that the coefficients for this would be 11, choose 0. That would be the first one, right? And then something here. And then it would be 11, choose 1. And then some other part here, right? So you're seeing this pattern forming. It goes all the way up to 11, choose 11. See that? So that's the coefficient part. And whatever your n is, that's what you put right here, and you just start at 0 and you keep going. Now, that's the first part. What's the next part we need to recognize here? Let's go back to our simple expansions and see if we can figure out. Now these are getting pretty messy, so I'm just going to erase some of this stuff here now. Okay. Let's see if we can figure out some other patterns. Okay, some other patterns here. So let's take a look at a plus b squared. So I have, well, I know these 1, 2, 1. Got that. And we said that the first term here is always taken to this power, and that's what the first term is comprised of. And the last term is always this one. But what about the middle terms? Well, so far we have this one times this one for the middle term. See that? A times b, along with that coefficient. What about over here? I want you to notice what is happening to the a variable in each of these terms. It's decreasing in degree, right? It's decreasing in order of the exponent. So here we have a cubed, then we have a squared, so decreasing by 1 sort of whole number each time. A to the 1, and what is this? A to the what here? Yeah, it's a to the 0, because it's just 1. So that's interesting. What about the other term here? What about the b? What's happening to the b term? Yeah, it starts at b to the power of 0, then b to the 1, then b to the 2, finally b to the n. You see that? So couple that together, Pascal's triangle, or the combinations, and the fact that the terms the terms of the binomial are to the power of 0 in the first term, and then the 1, and then to the 2, then to the 3, and so on for that first term, and reverse order for the second. You have something called the binomial theorem. We can use something called the binomial theorem to expand any power of a binomial expression. Now, a theorem is sort of like an idea or a set of rules that will help you do something, right? And something that's established, that's a repeated pattern, that's something you can rely on every time. So now this looks pretty complicated, but let's just break it up here. Okay, you have x plus y to the power of n, and the coefficients are n choose 0, n choose 1, n choose 2, and so on, all the way up to n choose n. That we've established. That's Pascal's triangle numbers for the this nth row or its combinations. The next part is this. The first term is x. And so in this whole first term, that x is taken to the power of n. Then that x is taken to the power of n minus 1. We keep subtracting until we get to the power of 0 here for x. finally, when we're recognizing this pattern and exploring this theorem, we then take the second term in the binomial, which in this case is y, and in the first term it's to the power of 0, so it's not there at all. Okay? You don't even have to write it, it's not there. But then y starts to creep up with this exponent, y to the 1, then y to the 2, and all the way to y to the n. We're going to do a simple example that we've already done. So when you're done writing that out, I want you to copy this out. A plus, actually let's do a plus b to the power of 3, and we're going to use the binomial theorem. I know we've already expanded it out, no problem. We're going to use the binomial theorem to see if we can go directly to the finished expansion. So we're going to do this according to the formula. So n is 3, so I'm going to do 3 choose 0. Then I'm going to do a, that's a to the power of 3, and b to the power of 0. And that's my first term. Now I'm going to simplify this later. But that's what you write for the first step of work. And if I'm asking you to expand this using the binomial theorem, you have to show this. All right? You have to show this. I need to know that you know what you're doing. So the next one is 3 choose 1. And then we have a to the power of 2. That goes down. B goes up, exponent to the power of 1. Then we have 3 choose 2. A cubed, b to the 0. Something doesn't look right. I skipped one, sorry. I'm like, wait a minute. 3 terms here. A3, A2, I'm sorry, I went the wrong way with A. I got distracted, sorry. This is 1, this is 2. Then it's 3, thank you. 3 choose 3. This is a to the 0, b cubed. That's better. All right, so we simplify this. And 3 choose 0 is 1, a cubed. And b we don't have to write. And as a matter of fact, you don't have to write the 1 either as a coefficient. Plus 3 choose 1, we said was what? 3 a squared b. You don't have to write to the power of 1 in this step. 3 choose 2 is also 3 a b squared plus 1 b cubed, and because 1's the coefficient, we do not have to show it. All right, so that should be the expansion right there. Now, is this what we had before when we did it manually? Looks pretty good right there. It's the same as this right here. Okay, binomial theorem. Now, the last and final just kind of note here from your textbook, and the key ideas right here, okay, says this, that you can determine any term in an expansion using patterns without having to perform the entire expansion. So we could expand the entire expansion a plus b to the power of 10. We could do that. We don't have to multiply it out manually. We could use those. We could use the binomial theorem. But you could also just pick the fourth term in that by using the patterns, right? The coefficient, right, would be 10 choose 0, 1, 2, 3. 10 choose 3 would be the coefficient. It would be a to the power of 0, 1, 2, 3, a cubed. It would be b then to the power, and so on. Okay? Actually, a would be 10, 9, 8, 7. A would be to the power of 7. B would be to the power of 3. One more final thing that I'll just note for you. Oops. Let's go back to the notes. Okay. Here's one other final thing that we should write for a pattern. Okay. Final note. But notice how the exponents, okay, the exponents always add up to n. The exponents on the variables add up to n. Now that is when we have a single monomial here. Okay, we're gonna do an example in the first step anyways, they should add up to n. So in first step of work shown, exponents on terms should add up to n. Okay, in first step of work shown, so that would be this step right here. Okay, before we've expanded each individual term, they should add up to n always. So we've got 3 plus 0, 2 plus 1, 1 plus 2, 0 plus 3. Okay, we'll do one more example here, and then we should be done for this lesson today. So in this example, we're going to use the binomial theorem to expand. Awesome. Okay, so those are our two terms, and this is n, right? So in our first big term, what we're going to want is we're going to want what? We're going to want a coefficient. That's going to be 4 choose what? 0. Okay? 4 choose 0, which is, yeah, going to be 1, right? But let's use that format of the binomial expansion. 4 choose 0. Now we're going to have 2a as a term to the power of 4. So you can kind of see where if we have anything other than just a single variable, we're going to have to do a little bit more work here. But not bad. Now, this is minus 3b. That's the same as plus negative 3b. So for your second term, you're going to have to include the negative sign there. And what is my exponent here? 0. Very good. Okay, awesome. That's the first term that we're going to simplify later. So now we're doing 4 choose 1. And now we're just dealing with the exponents now. So 2a, that drops to 3. And negative 3b, that rises to 1. You guys with me here so far? Okay. I'm going to freeze the screen here, and why don't you go ahead and see if you can write the rest of the terms out. Okay, so I'll just freeze the screen in class here, and I'll finish the expansion here as well for this line of work. Okay, when you're done, you can look up at the board for that first step. And then I want you to go ahead and simplify to get your final step. And I'll do that on the board too while the screen is frozen again. And let me know if there's anything in there that you think I've missed.